Hey everybody, welcome to chapter 14. This chapter is about correlation and simple linear regression. I know that sounds really confusing, but if you remember way back to chapter 3, we learned about correlation, the correlation coefficient and covariance at that point. And so really all this has to do with is comparing variables where there's an x and a y variable. So the first thing you need to understand is the difference between what's called a dependent variable and an independent variable. So x is always the independent variable, and y is always the dependent variable. What that means is that changes or variations in x explain variations in y, but not in the reverse. And I'll give you an example of that in a moment. So when we do correlation analysis, we're trying to measure the strength and the direction of the relationship between two variables. You can see these two examples they have here. The first one on the left, that as x goes up, y goes up. We would call that a positive linear relationship. The one on the right, as x goes up, y goes down, we would call that a negative linear relationship. So here's an example. A new car dealer wants to examine the relationship between the number of TV ads they run per week and the number of cars that they sell that week. Okay, seems like an intelligent thing to try to measure, right? So we're going to assume that the more ads that we run, probably the more cars will sell. So we would think that a change in the number of ads would lead to a change in the number of cars sold, not the other way around. We wouldn't think, hey, if I sold more cars, then I would run more ads. That doesn't make any sense at all. So that means that the number of ads is the independent variable. And so we're going to put that on the x-axis. And the number of cars sold is the dependent variable. That's the y. So here's their sample. 6 weeks. They ran different number of ads each week. And not a different number, but they ran a certain number of ads each week. And then there's the number of cars sold. And we do a scatter plot, and it sure looks like there's a positive linear relationship there, right? You can see that generally speaking, as we run more ads, we sell more cars. All right, so in order to do a correlation analysis, at least to do it manually, we need these 5 pieces of data. We need the sum of x, the sum of y, the sum of xy, the sum of x squared, and the sum of y squared. This just tells you what I just told you, that every calculation we perform uses this. Did I say 5? Well, okay, I said 5 numbers, and then we add n to make a 6-number summary. All right, so the first thing is the correlation coefficient. We learned about this way back in chapter 3. It's denoted with an R, and its values range between -1 and +1, with -1 being a strong negative relationship, +1 being a strong positive relationship. When the R equals 0, there's no relationship. So there's some examples of each. You can see 1 and -1, and then how it becomes more spread out as things go down. So here is the formula for the correlation coefficient. I laugh because you're going to love it. Whoa, that looks insane, right? It's actually not that hard if you think about it. It's just all those numbers. It's n times the sum of xy minus the sum of x times the sum of y, divided by the square root of n times the sum of x squared minus the sum of x squared times n times the sum of y squared minus the sum of y squared. So like if you had that 6-number summary, it'd be pretty easy. You just plug them in here and you could make it happen. It wouldn't be that bad. Luckily, there's a function in Excel, which is correl for correlation, and you do array 1 and then array 2, where array 1 is your x data and array 2 is your y data. And it'll give you the same answer. All right, so R, what we just learned about, is the correlation coefficient of a sample. The population correlation coefficient is, well, the correlation between all values in a population. As you can imagine, it's pretty rare that you would actually be able to do that. So mostly what we're trying to do is use R to approximate the population correlation coefficient. So we can use a hypothesis test to determine the population correlation coefficient is significantly different from 0. So here's an example. Right, we can develop a t-test statistic where R, which is our sample correlation coefficient, divided by, well, you can see the formula. I won't read the whole thing to you. But that gives us a t-test statistic. Then we figure out the critical t-score using the t-distribution. When we're doing this, because we have multiple variables, right? Everything in the past, we've just had an x variable. Now we have an x and a y variable, so our degrees of freedom are n minus 2 rather than n minus 1 like they were in the past. And then we just use t dot inverse, and we can find our critical t-score. And then we can compare our critical t-score. So this is a lot like we've done in chapters 7, 8, and 9. Compare our critical t-score with the t-test statistic that we calculated. So in this case, our t-test of 3.047 was greater than the critical t, so we would reject the null hypothesis. We would say, wait a minute, that correlation coefficient is so far away from 0 that we can't, on the sample, that we can't really assume that the population correlation coefficient would be 0. So there is, in this case, a positive relationship in the population between the x and the y. That's what all that means. But as you work with it, it'll become simpler. So simple regression analysis. Here's where we take a scatter graph like we just had, x and y data, and we determine the best straight line to fit the series of ordered pairs. This is simple regression, and it's as far as we're going to go with it in this class. So here's our formula. That's called a y hat. Y hat means the predicted value of y for a given value of x. And then we have the slope of the straight line plus the y-intercept times the x variable. If this reminds you of something from like an algebra class, like the formula for a straight line, y equals mx plus b, you're right, it's the exact same thing. Except now we call it y hat equals b1x, where b1 is the slope, plus b0x, where b0 is the y-intercept. And so for any value of x, we could calculate an expected or predicted value of y. There's for a population. It's actually very similar, except we include something called the residual. But don't worry too much about this, because really our focus this chapter is not working with populations. But we will need to know a little bit more about the residual. All the residual is the actual value of y at a given point minus the predicted value, what we thought it would be. And you'll see more as we work with it. So you can see, like in this example, we observed a certain y, but according to our line that we calculated, we had a predicted value of y, and the difference between the two is what we call the residual. And like I said, don't worry too much. It'll come together as we do more. All right. So the least squares method identifies the linear equation that best fits a set of ordered pairs. So the goal of using least squares is to minimize the total squared error between values y, so the actual y, and the y hat, or the predicted value of y. And it's the sum of each value of y minus the y hat squared. And that's called the SSE, or the the sum of squares error. Sorry. I had to pause for a moment. All right. Here's the formula for calculating the slope and the y-intercept manually. Again, as scary as that looks, if you had that 6-number summary, it wouldn't be that bad. You could do it. It's just plugging numbers in. But not very often that we're going to do this manually. Okay. You're going to have access to technology when you're working this type of stuff out, unless you happen to be trekking across the desert and you decide you need to calculate a regression line and don't have Excel or something handy, then I guess you'd have to use this formula. But I'm guessing that's never going to happen. In real life, you're always going to have a computer available to you. So one of the nice things is, I'll show you in a minute, that you can use Excel to do a lot of this work for you. So in this case, they calculated it all. This is still our car sales and TV ads data. Okay, and there's the 6-number summary. They were able to calculate the slope and the intercept, so that gives us an equation, right? So the y hat, the predicted value of y, you could just plug in any value of x and you could calculate the predicted value of y. There's what the line looks like. And now, for example, at 5 TV ads, that's our x, we would expect our predicted value, or our point estimate as it calls it, would be 23.95 for the number of cars sold. Cool thing is we can use Excel to do a lot of this work for us. When we go through the guided problems, I will do this for you so you can see how it's done. But in essence, you put the data in the worksheet. You go to your data analysis tools that we've already used, except now, instead of choosing, I forget the analysis we used before, we scroll down and we use regression. And then when we go to regression, it asks for our y range and our x range, and we have to choose labels if we're going to include our labels in our x and y. And then output range tells Excel where to put the information it's about to give us. And this is what the output will look like. So the thing that it labels multiple R, that is correlation coefficient. So instead of having to, do a separate function for it, that's right there for you. And the thing that's labeled intercept under the coefficients line is our y-intercept. And the thing that's labeled with the x value, in this case number of TV ads, that is our slope. Our total sum of squares, which will come up as we do some of this work, is just our sum of squares regression plus our sum of squares error. And here again are the formulas. Here they tell you they're giving you a calculator-friendly version of the formulas. That's nice of them. But honestly, that same output that we just produced by going to regression, it gives us these. So if you go under the column heading for SS, the thing that's labeled SS or regression is our SSR, sum of squares regression. The thing that's labeled residual is our SSE, or our sum of squares error, and then the two add up to be our sum of squares total. There's another measure that we use sometimes. It'll measure the percentage of the variation of the dependent variable that's explained by the independent variable's change, so it comes out as a percentage. And here we just take our sum of squares regression divided by our sum of squares total. Okay? That's called the coefficient of determination, or sometimes R squared. So for the car sales data, 0.6995, that means 69, almost 70% of the variation in car sales can be explained by the TV ads. And then, which is really good to know, right? Because that means 30% of that variation is being caused by some other factor. I don't know if cause is the right word. Cannot be explained by the TV ads is probably a better way of putting that. All right, so we have all this data and we can draw this straight line, So if you think about it, that puts us in a really great position to say, um, you know, can I make a prediction based on this information? In other words, if I know that at this level of ads, I have this many car sales, can I make a prediction for, say, adding more ads, and will it hold true? So we know that, like we said, that we have these point estimates that we can calculate, and we can use the regression equation to do that. We can also construct a confidence interval around the point estimate so that we have an idea of how much we can rely on that. And to do that, we calculate something called the standard error of the estimate, which is just the sum of squares error, the square root of the sum of squares error divided by n minus 2. So here, if you take a look at these two lines, you can see one has more error than the other. So the one on the left has a small standard error, and the one on the right has a larger standard error because it's more spread out. All that means is that, again, the likelihood of the difference between what we predicted the value would be and what the actual value would be is going to be greater with a larger standard error. Again, our Excel output has that calculated for us as standard error of the estimate. It's just labeled as standard error. So to calculate a confidence interval, as you can see, again, it's a big, crazy math formula. And guess what? For this one, well, we kind of have to just do the math. There's no function in Excel that I found that will do this for you. But if you take it piece by piece, it's not that big of a deal. So you have your y hat, your predicted value of y for the desired value of x, plus or minus your critical t, times your standard error, times the square root of 1 over n plus x minus x bar squared, divided by the sum of x squared minus the sum of x squared divided by n. Again, if you plug the information in, it's just basic math, okay? So don't let the look of that formula scare you. So there's the example. We have all the data we need. Calculate it all out. And that gives us an upper confidence limit of 28.748 and a lower of 19.152. It's pretty doable, trust me. So what that's saying is, for example, here with 5 ads, that was our value of x that we were looking for. We believe that we're 95% confident that the number of cars we'll sell with 5 ads is somewhere between 19.15 and 28.75. So we did what was called a confidence interval. We can also do what's called a prediction interval. So when we do a confidence interval, that's for an average number of cars sold all weeks. In a prediction interval, we're saying we think that we're going to try to predict for an individual week. And if you look at it, it's the exact same formula as the confidence interval, with the exception of we add 1 here. And I will be flat out honest with you that I don't know why, or I'm sure someone better versed in statistics math could tell you why the number 1 is the number used there. But if you think about it, since we're multiplying it by the square root of that, all that happens by us adding that 1 is that we're going to add a certain amount of variability to this. In other words, our limits, lower and upper, are going to be higher and lower. So we're going to say we're less certain for the prediction of any specific prediction interval than we are for a confidence interval. Again, it's just math. Crank the numbers, and you'll see 35.88 and 12.02. That interval is so big for this example that it starts to not be very valuable to us, right? If I do five ads, then I predict I'll sell somewhere between 12 and 35. And I'm guessing that with the cost of doing 5 ads, that selling 12 would be unacceptable and 35 would be great. But all that really means is we're 95% confident that the number of cars sold in a particular week in which 5 TV ads are used will be between 12 and 12.02 and 35.88. One last kind of thing to remember, that we can't really predict values of the dependent variable beyond the range of x. Why? Because we don't know that the straight line relationship that exists with the current x values we have will continue to exist beyond that. So we can't make that assumption. The results will be, like it says, of questionable value. And we have to remember not to confuse correlation with causality. And what that means is just because there's a relationship and that we say that relationship explains the change in x explains some of the change in y, it doesn't necessarily mean that x is causing y, right? And that's a major difference. I think it's part of a challenge we have in our world right now, where we think that we know so much that we assume there's causality between things just because they're correlated. And that can range all the way from gun control debates to global warming debates and to every other major debate that's out there, that sometimes we're assuming things are causal when they may not be. They might just be correlated. Anyway, so that's the end of this chapter, or this lecture at least. I hope it was useful to you, and good luck on the homework assignments.